We ended the last video talking about a basis for a vector space V. So we said that the vectors v1 through vn form a basis if you can show two things: that the vectors are linearly independent and the vectors span your vector space V. We also mentioned that a basis is the minimum number of vectors that span your vector space and the maximum number of vectors that are linearly independent. We gave the example R3, and we said that the standard basis for R3 is E1, E2, E3, which is just the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. This one is very obvious to see that this is a basis because you can see that these are linearly independent and that they span. We also said that a vector space can have infinitely many different bases. We just need to make sure, depending on the dimension of the vector space, which here is going to be 3, which is the number of vectors that needs to be in the basis. We said that we need to make sure that we have linearly independent vectors, 3 of them, and that the 3 vectors span R3, then that will be a basis. So we showed that this set of vectors in R3 forms a basis for R3. And here's the work. We first showed that they were linearly independent by showing that C1, C2, and C3 have to be equal to 0 in order for this linear combination to equal the 0 vector. And then we had to show that these vectors span our vector space. So we wrote a linear combination of these 3 vectors, and we chose the vector A, B, and C. This corresponds to any vector in R3. And we put this matrix into reduced row echelon form, and we found out that we can write alpha 1, alpha 2, and alpha 3 in terms of A, B, and C. And we said that if it didn't span, then we would get an inconsistent system. We would have something like a row of zeros and then some non-zero number here. So this is another basis for R3. Whenever we have two bases for the same space, then if one basis is V1, V2 through Vm, and the other basis is W1, W2 all the way to Wn, then M has to equal N. We have to have the same number of vectors in both of the bases. Suppose we have a basis for a vector space, so we know that the vectors V1 through Vm is a basis. Then V is finite dimensional, and we say that the dimension of V is equal to M, the number of vectors in the basis. So like R3, you know that's a 3-dimensional space, and that's because you can find 3 vectors that are linearly independent and span the vector space R3. Now, it is possible for a vector space to be infinitely dimensional, meaning that there's an infinite number of vectors in its basis. So if V is infinite dimensional, that implies the dimension of V, you can write it like this, is infinity, which means there are infinitely many vectors in the basis for V. In this class, we're not going to really talk about infinite dimensional vector spaces. We're going to just talk about finite dimensional vector spaces. So we're always going to have a number here for the dimension of V. Okay, let's move on. Let's talk about some standard bases. So for Rn, the most natural basis for this space is 1, 0, all the way to 0, which we're going to call E1. 0, 1, 0, all the way to 0. There's going to be n entries in each column. This is going to be E2. 0, 0, 1, 0, and so on. This is E3. All the way to 0, 0, 0, 1. And this is going to be En. You can see that these are linearly independent, and they're also going to span your space. So this is the standard basis for Rn. And because there are n vectors in the basis, the dimension of Rn is n. For P sub n, remember that this is all polynomials of degree n minus 1 or less. So in set notation, we can write this is equal to a sub 0 plus a1x plus a2x squared, so on. This is what the polynomials, when you evaluate them at on x, look like. All these ai's belong to the real numbers. And the standard basis for this space, let's also call this B. The standard basis would be 1, x squared, x cubed. Sorry, this should be n minus 1 here. X to the fourth, and so on until you get to x to the n minus 1. You can see that these vectors, they all belong to the space of all polynomials of degree n minus 1. We can see that they're linearly independent because you can't get x from 1. Remember that the only thing we multiply these vectors by are scalars, real numbers, so you're only going to multiply them by like a 10 or something. So there's no way to get an x here or x squared, so they're linearly independent. And they also span our set here, our vector space, because any polynomial of this form can be written as a0 times 1 plus a1 times x, and so on. So this is the standard basis for P sub n. And what is the dimension of P sub n? Well, how many vectors do I have in the basis? I have n of them, right? 1, 2, 3, all the way to x n minus 1, but remember we have this 1 here, which is an extra vector. So there's n. That's why we call this P sub n. This n corresponds to the dimension of the space, which is always one more than this one. What about the vector space consisting of all m by n matrices? What do you think the standard basis looks like? Well, if we have an m by n matrix, we're going to have m rows and n columns. We can put a 1 in the very first entry and zeros everywhere else. So the only thing that's non-zero is this first entry. And we're going to call this matrix E11. This 1, 1 corresponds to where you're putting the non-zero entry, this 1 here. And then you just move the 1 along the row. And this will be E12. And you just continue this. So we can put a bunch. In fact, let me write it like this. Dot, dot, dot. 0, 0, all the way to 1. This will be E1N. And then the next one would be with a 1 down here. And this is E21, and so on, all the way until you get to a 1 here. And this is EMN, because this matrix is an M by N matrix. I don't think I can make this much smaller, but I'll try. Let's see. Try to fit it all with, so you can see it. That doesn't look too bad. So that is the standard basis. So how many vectors are in this basis? Well, think about how many 1s we're going to write. We're going to put a 1 in every single entry of this matrix, this M by N matrix. So there's M rows and N columns. So we should have M times N vectors in the basis. So the dimension of this space is M times N. Now we're going to talk about a very important theorem. This is something you're going to use a lot. Suppose V is a vector space and the dimension of V is equal to N. Suppose that you have N vectors in V and you want to figure out if they're a basis. As long as you have N vectors, and you know, because this is going to be a vector space you know pretty well, you already are going to know a basis for this vector space. But now we're picking some other vectors and I want to figure out if these vectors also make a basis for your vector space. Well, these vectors, if they span V, then the vectors are linearly independent. And if they're linearly independent and they span V, then W1 through W2 through Wn forms a basis. For V. This is really important. Let's talk about this. So you know that the vector space has N vectors. So you have to have N vectors for this to work. And if you have N vectors, you know that a basis is going to span and it's also going to be linearly independent. So if you can show that these vectors span, then you get that they're linearly independent for free. And that would mean you form a basis. So you only have to check one thing. You can either check that these vectors span or they're linearly independent. And we know from a problem we did in the last video that spanning takes some time to check. Checking that vectors are linearly independent is a lot quicker than showing they span. So if I give you, for example, R3, and I give you 3 vectors, and I ask you, do they form a basis? Well, since we know the dimension of R3 is 3, all we have to do is check if the vectors are linearly independent. If they're linearly independent, then you know they span, and then you know they form a basis. The proof of this is in the book. If you're interested in it, we're just going to use this fact. So in other words, if you have that the dimension of V is equal to n and a set of n vectors, and you show they are linearly independent, then you get spanning for free, or vice versa. So if you check that they span, you get linear independence for free. Let's look at our first example. Let's say that V is equal to R3. I want to know, does this set form a basis for R3? To solve this problem, we need to remember the standard basis. The standard basis, B, is E1, E2, E3. We also said that any other basis for V would have three vectors. This set has 4 vectors. Since it has more than 3 vectors, then it's not a basis. Remember that you need 3 vectors, and 3 vectors would be the minimum number of vectors that would span the space, and 3 would be the maximum number of vectors that are linearly independent. So what's going to happen if you check this, you're going to show that these vectors are not linearly independent. Okay, now we have, for R3, we have this set T. T has 3 vectors. So that means it's possible that T forms a basis for R3. To figure it out for sure, we just need to see if they're linearly independent. So let's call this one V1, V2, V3. Are V1, V2, V3 linearly independent? Okay, to check this, we just put these columns in an augmented matrix with 0, 0, 0 here, and find the reduced row echelon form. We just want to see if the reduced row echelon form is the identity matrix. So to do that, 1, 2, 3, 0, let's multiply row 1 by -2 and add it to row 2. And we get 0, -3, 3, 0. And then we're also going to multiply row 1 by -4 and add it to row 3. And we get 0, -7, -12, 0. The next thing I'm going to do is I'm going to divide this row by -3. And I can also divide this row by -7, but I'm going to leave it. I'm going to leave this at -7, -12, 0. Now I'm going to get rid of this -7, so I'm going to multiply the second row by 7 and add it to row 3. And I'll get 0, 0, -19, 0. So 7, -7, yeah, I think that's right. And then we can just divide this one by -19. In fact, let's just go ahead and do that. Okay, and I really don't have to go any further because I can tell that, see, I have 3 pivots, 1, 2, 3, and I can zero out everything else. So the reduced row echelon form of this matrix here is the identity, which tells me I'm going to have one solution, which tells me that C1, C2, C3 is equal to 0 for C1, V1 plus C2, V2 plus C3, V3 equal to 0, where this is V1, V2, and V3, which tells me our vectors V1, V2, V3 are linearly independent. And because they're linearly independent, then they span because there's 3 vectors, and that tells us that T is a basis for R3. So they're linearly independent, which tells us it spans, which tells us that T is a basis for R3. Let's look at another one. Here I'm working with R3 again, and I tell you U is these 2 vectors. Can it be a basis? This one shouldn't take you any time because we know that a basis must have 3 vectors. Because we only have 2 vectors, there's not enough vectors for you to be a basis. So the answer is no. Remember that you need 3 vectors for you to span R3. So there's not enough vectors in you to span R3. Let's switch vector spaces. Let's talk about P sub 4. Now let's recall what this is. This is all polynomials of degree 3 or less. And we know that the dimension of P4 is 4, and we know that a basis is 1x, x squared, and x cubed. We want to know if S, which is equal to this set, is S a basis for V. Okay, so how do we figure this out? We need to see if these vectors are linearly independent. Because there's 4 vectors, so it's possible that it is a basis. Well, let's see if they're linearly independent. Remember that linear independence means that we can't write one vector in terms of all the other vectors. Notice that this one is a 3. And this one has an x, this one has an x squared, and this one has an x cubed. So there's no way that I can get an x cubed from adding these multiples of these vectors together. There's no way that I can get just a 3 from adding multiples of these 3 together. There's no way that I can get this one from these 3, and there's no way that I can get this one from these 3, because there's no x term in these. So I can already tell just by looking at them that they're linearly independent. But there's another way to do this. What you're going to do is kind of think of these vectors as vectors in R4. So let me tell you what I mean. I'm going to write a column vector. And what I'm going to put in the first entry is the coefficient in front of the 1. In the second entry, the coefficient in front of the x. In the third entry, the 1 in front of the x squared. And in the fourth entry, the coefficient in front of the x cubed. So we're kind of thinking of these as vectors in R4. Now, of course, you can change the order of these. You can make this x and this 1, or however you want to do it, as long as you stick to the same ordering for all of these vectors. So we can think of S. So I'm going to keep this here because we're going to use it. In fact, let me move it right here. So we can think of S in this way. We have just x. So this is 0 plus x plus 0x squared plus 0x cubed for x. So this would be 0, 1, 0, 0. This one, and this with the same idea here, would be 1, 0, 1, 0, because it's 1 plus x squared. The next one is 3, 0, 0, 0. And then the last one is 0, 0, 0, 9. Now looking at these vectors, can you tell they're linearly independent? Well, again, you can't get this 9 from any of these because I don't have a 1 in any of these entries. So that means I can't get this vector from these 3. Can I get this one from these 3? Well, this one has a 0, this one has a 0. This one has a 1, so I could multiply this by 3, but if I do that, I'll get a 3 here, and there's no way to get rid of that 3. So I can't get this vector from these. I can't get this one from any of these, and I can't get this one from any of them, so they're linearly independent. Again, you can put them in a augmented matrix and try to get it in reduced row echelon form, and you'll see that the reduced row echelon form is the identity matrix. So they're linearly independent, and that tells us that this set is linearly independent, which means they span, which means they're a basis. So the answer is yes. Linearly independent implies span, which implies basis. Now remember, in general, linear independence does not imply a spanning set. It's only true if the dimension is equal to the number of vectors in your set. I've got one more for you. 1 plus x, 1 minus x, x squared minus 4x, x cubed plus 1. And v is the polynomials of degree 3 or less. Remember, the dimension of v is 4. Maybe pause the video and see if you can figure out if these vectors span and are linearly independent and form a basis for v. So is T a basis for v? Okay, by looking at it, it might be a little difficult to figure out. So let's try that trick we did before where we write them as column vectors. This corresponds to 1, this is x, x squared, and x cubed. So then T is 1, 1, 0, 0, 1, negative 1, 0, 0, 0, negative 4, 1, 0, 1, 0, 0, 1. And all I need to check is if these vectors are linearly independent. So I can put them in a matrix. 1, 1, 0, 0, 1, negative 1, 0, 0, 0, negative 4, 1, 0, 1, 0, 0, 1. Get this matrix in reduced row echelon form. 1, 1, 0, 1. Subtract row 1 from row 2. So this is -2, -4, -1, 0, 0, 0, 0. Here I have a pivot, and that will zero this one out. So I can put a 0 here. 0, 0, 0, 1. But here I have a pivot, and that will get rid of these two, so I can get rid of those. And then I can divide this by -2, and I'll get another pivot, and that zeroes this one out. So the reduced row echelon form is the identity matrix, which tells us that the vectors are linearly independent, which implies a span, which implies they are a basis. And we're done.